is additive manufacturing, right? So there are several slides, and I hope you guys enjoy this the slides. They are not mine. They are from the NSF or from the other professors. Today we are going to move on to the next topic about laser machining. The laser machining, we talk about the laser femtosecond, the laser micro, and/or is the nano machining. And Dr. Lei, this lay is not our lay. Okay, so this lay is my research, long-term research collaborator, and this is Dr. Lei was my committee member when I was a doctoral student. So I would have published many papers. So these slides, I asked him for these slides, and he gave this presentation at several universities. So it's free for me to introduce these slides to you guys. So femtosecond. What is the laser? Have you ever? So I think you guys have heard laser, right? Laser. What is laser? What is the academic name of laser? So here, the laser is an acronym. It is named. It is called light amplification by stimulated emission of radiation. A laser is an optical or this amplifier. So this so here this is excited value, excited level, and here is the ground level of energy. So before these items in excited state. So here is the ground level, and here is the excited level. So here is the before emission and during emission, and this is the photon. Okay, you know photon, right? Photon. The light, all these lights will give out the photons. The photon, so during emission, and here this is the excited level, excited this item and goes down, and then energy is released. So after emission, so this is a wave coming. This is a wave here, and item in the ground. This item goes from the high excited level and to this level. So this is energy. The energy difference between these two states is called this delta E, and this is H. This is nu. This is laser. So the first laser in 1917. So this is 1917, and Albert Einstein, and a very famous person. Professor Einstein laid the foundation and for the laser when he introduced the concept of stimulated emissions. And so this is a very so have you learned this is the light, the photons in the physics? Okay. So the photons, this is a photon. This, for example, the dual, this is the rho of this is the wave, and with this photon, it can be this photon and also a wave. Light is a photon and also a wave. And another professor, Theodore Mammon, is developed the first working laser at the Fuji's research lab in 1960s. So this is in 1960s. This is the first the working laser was developed. You can see, and we people had this is the theoretical foundation first, and then engineers. I will think I do not know is a Theodore Mammon, but I assume he is an engineering professor, maybe the physics professor, and he based on the principles of this laser, and he developed the first functioning laser system. So here's a very awesome. So this is Dr. Theodore Mammon in the Fuji's research lab with the first working laser. These are components of the first laser. We have the laser beam, and we have this ruby crystal, and this ruby crystal comes a flash tube, and this 100% reflective mirror, and this polished aluminum reflecting cylinder. So the aluminum. So this is 95% reflective mirror. So here's the switch, and definitely need the power. Okay, power power supply is needed because energy is conserved all the time. So laser parameters, as here are several important laser parameters. First one is the laser power, the energy level, the laser power P, and the laser intensity. Laser intensity is the laser power per unit the area. Metal is the intensity. The wavelength, and this wavelength lambda, and the Gaussian beam profile. Usually the beam metal is distributed in the bell-shaped the distribution. The Gaussian beam profile. And beam spore size, when it is something, and what is the size of the spore, the beam spore size. The beam width is a W0, and this relay range then a measure of depth of focus, M squared, and beam quality factor, a deviation of the laser beam from a theoretical Gaussian beam. So this is very important. This factor here. And the Gaussian beam profile. So Gaussian beam profile here. So here the Gaussian beam profile means this is the spore size. You can see this is a laser spore. And this is the Gaussian beam means the energy distribution. Okay, the energy distribution for this laser beam is based upon this is Gaussian distribution. And so this is one. This is a radial distance from here to here. The radial distance. So this is the total power. And here is one distribution. I have a laser system in my lab, and for my laser system, my laser system does not have laser beam profile. It's a Gaussian beam profile. What it has is very flat one. Go here, flat, go down. Okay? So that means my laser system is much more sophisticated than this is original one. So this is original is a Gaussian beam distribution. And so here, this is the beam width. This is the relay range from here to here. And so here is another one. This is W0 width, laser going out from here. So here is one distance called the relay range, and here is another one on another side. The relay range versus this is the beam width. So this is the distance from the width, and here is the beam. This is the diameter. It's the beam diameter means the beam spore size. So here is a beam spore size. Okay, how big the spore size is. So definitely here is a beam width. The longer your distance is away from this W0, and the bigger the spore size is. Right. So here is a comparison between the common light, the hour light, this light, and versus this is the laser. For common light sources, we can see, for example, the sunshine, light bulb. We are using collimated light bulb. This floodlights, and this light emitting diode and hot object. Object very hot, and it will shine. And laser, this is the common light sources. So these are unique characteristics of this laser beam. Where laser beam is a monochromatic and single wavelength, and coherence means that consistent phase between all light elements. So temporal, this is about time. Continuous wave to femtosecond pulses. Femtosecond means 10 minus power minus 15, right? Femto. 10 power minus 15 is a femto. The pulse is very short, ultra fast. This is a laser. It's highly concentrated, unfocusable, and to extremely small spores. The beam irradiates the profile. The unique spatial is a spatial, the space. Unique spatial power or energy distribution. So then we first talk about this is the chromaticity. So the different wavelengths is a color. Okay, we have a color different wavelengths. So this is a white light source. So we have different color. So this is the same wavelength, This is the monochromatic light source, and this is laser light source. You can go. This goes. It's very consistent. So then the coherence and the directionality. Coherence. The two beams of light are coherent, and when the phase difference between their waves is constant, and they are non-coherent if there is a random or changing phase relationship. You know, phase that is a wave. I told you guys the light has two the poles. The pole number one is it behaves like a wave, and pole number two is it behaves like the photon particles. Right? You know the pure characteristics of the light, right? Wave and particulate. Wave light and particulate. So here is a wave, light wave. So here is wave. Let's say these waves and the phase difference between these waves are constant, and so we call this a coherence. So here is randomly these are four waves, and the phase difference is random, and this is called incoherent. So here is some examples: a laser beam and coordinated photons, and coherent. This is the light waves. So here is an ordinary light we are using, and this is the unorganized photons. You can go always right in all these directions. And this is incoherent light beams because we are pulling in all directions. So there is some time difference. As a result, at given any point, all these waves will have very different phase for any given common point. That is the reason this is called incoherent light waves. But for this case, the things are contrary. Look at here. So this is collimated photons. These photons, and they just focus on one very narrow band. So here is these waves, and they can be coherent, the waves. So this objective for this talk, I want to use Dorley's what Dorley presented and to entertain my students. Okay, so how to develop femtosecond laser beam micro nano machining system. And the fundamental study. So fundamental study, laser matter interaction. So how the laser interacts with the matters, with substance. Effect of process parameters on part quality, etc. So these are fundamental research. So another one is that technology development, micro nano machining technology techniques for various applications. For example, capillary, energy, and these microfluidics, etc. So these are fundamental research, and then develop some specific technology for some specific applications. So micro nano machining approaches. So lithography, one is lithography, one is machining. Lithography, and they use photolithography, extreme ultraviolet, electron beam, lithography, X-ray, lithography, and salt lithography. So machining, mechanical machining, and we have learned, right? We have learned non-traditional machining, and we talk about the EDM. So definitely laser machining is another type of non-traditional machining. You can see these. Okay, so for example, this is a silicon substrate here. So this is a masking film. This masking film is silicon dioxide, and also silicon 3, and this is an N4. So coating with photoresistant, and this one photoresistant, then this is a photoresistant salt the bake, and then mask is alignment. This is mask alignment, and then the UV, the ultraviolet. Then here expose, and this is the post bake and develop, and then etching, and finally and stripping. So here is lithography, and for this is machining is different. Why people want to use femtosecond laser? First, highly intense and focused ultra short this pulse. It is pulse. The duration of pulse is 10 power minus 15, and very precise and deterministic. And clear ablation and negligible HAZ. HAZ stands for heat affected zones. This is because the time is too short. The pulse duration is too short. So the heat does not have enough time to affect the neighboring area. So wide range of materials, this femtosecond can be used for wide range of materials. And machining in the bulk, this is can lead to the mass production of something. Look at here. So this is the beam. So here is a generated crater here. Right? So here is you can see this is another one is a beam, and so here is the focused ultra fast the pulse, the region of optical breakdown here, and so this is the hole diameter. This is a hole in the generated, and this is a laser small size. And so here is a hole. This is a nanometer. You can see this is a SEM. This is sorry. This is optical. This is optical. This is a holes generated using femtosecond laser. This is a total beam. This is a presentation in June 2015 in the Qingdao University of Science and Technology. So here is a femtosecond laser machining setup. So here's the laser system. The pulse laser system, oscillator pump, strengthener, amplifier plus pump, and compressor. And so here is a computer control, computer control. So this computer controls the stage. This is a stage, 3D positioning stage, and here is a sample. And so here is a laser system. And so here is a pinholes. It is a lens here. Beam is a shutter. So this is a polarizer, and here is a wheel plate, and here, and this is the here is a mirror, right? Here is an illuminator. So here is a monitor, and CCD. This is a camera, and this is a camera, and so here is another mirror. This is a lens, and the sample is mounted on this stage. So this is very, very similar to what we have in my lab, in my nanosecond laser lab. So our laser system is nanosecond. Here is femtosecond. And then we talk about laser-induced periodic surface structure. The first one, laser-induced periodic surface structure. You can see it's very, very beautiful without a layer. So this is the layer, you can see this is the periodic. And first observed in 1965 by Breton with the ruby laser. Ruby is the color of the laser beam. So subsequently observed with other types of laser and application for many materials. So this is for stainless steel, femtosecond laser, and linear polarization. And here, this is the density. Okay, you can see 1.4 joule per centimeter square. So here is analytical polarization. So this one. So here is another one, circular polarization. This is analytical. So here is the circular. So then, all I use the femtosecond laser to microfill high aspect ratio holes and through flexible and hollow cone fiber. So here, so to develop a new method to fill high aspect ratio micro holes with high quality and efficiency. What is a high aspect ratio? It means that one dimension of the hole is much larger than another dimension. Right? So this is the high aspect ratio. So approach and to use the hollow to comb this fiber as a simple spatial filter and to transmit the laser beam and to the target position to achieve high beam quality. Use the hollow cone fiber. Significance Femtosecond laser machining is the promising new technology for efficient production of high aspect ratio microstructures and with high quality and low cost, which will open up opportunities for many new devices and products in aerospace, automotive, electronics, and biomedical areas. So here's the key parameters. So here's the pulse duration. Pulse duration is 5 seconds. This is a focusing length. This is a beam focusing length and coming down. This is a hollow fiber, okay? This is hollow fiber, the stage 2 and stage 1, and then this beam comes through this hollow fiber and then come to this sample. This is a sample to fiber distance from here to here. So as a simple spatial filter, use a simple spatial filter to transmit the laser system to achieve high beam quality. This is used as a spatial filter. The spatial filter, these hollow fibers. So this is a fiber inner diameter. So this is a fiber inner diameter. So laser fiber coupling efficiency, laser fiber versus the pulse energy. So this is into the pulse energy micron tool. So here is the coupling efficiency. So here is output the pulse and is output the pulse energy. So this is the coupling efficiency. And so here is, here is output pulse energy, and here is the coupling efficiency. So laser fiber coupling efficiency versus bend angle. If you bend it, and they can affect this efficiency. You can see this is bend angle, and here is the output the pulse energy, output the pulse energy. So this is a coupling efficiency. So they are micron hole and with a good aspect ratio. You can see this is entrance hole, and so this is exit hole. Actually, this is one hole. One picture is from this side, another picture is from that side. So this, for this pulse energy is 1.35 micron joule, and pulse duration is 400 femtosecond, 3 femtosecond. My laser pulse duration is 5 nanosecond. It's much bigger than this one. Focal length 700, and so on and so forth. So this is a micron hole generated. So micron hole with minimal heat effective zone, as I said, because the time is too short, so this heat effective zone is very negligible. Here's a pulse energy. Here's a cross section. You can see. So here is a micron hole in this tool skill. Micron hole is generated. And tool skill, we know tool skill is very hard. This is generated. It also entrance and exit, the same 4 holes but different size. Here is a summary for laser micro drilling hole. So the coupling efficiency, because they use the fiber couple, the coupling efficiency is strongly associated with air breakdown. Beyond the breakdown zone, the coupling efficiency is very high and almost remains constant, and then gradually goes down within the breakdown zone. So the coupling efficiency is only slightly affected by the bend angle, and we see the bend angle changes. Then, thus, it can be said that the flexible fiber was fairly high tolerance for bending. So the flexible fiber. So the roundness and the repeatability of entrance micron hole are better than those of corresponding exit. This is a micron hole. This is understandable. This is as is the entrance, the energy, more energy, right? The technique to conduct micro drilling and through a flexible hollow cone fiber using a femtosecond laser can be used for hard materials, hard metals, or non-metal materials with the thickness of this micron hole. The 1 millimeter, if 1 millimeter, it can have control the micron hole. So this is first the research magnetic beams. And second one is they use the femtosecond laser scribing. Scribing means that is write something on the film. So this is a molybdenum thin film on flexible substrate and using XCOM is a focused beam. So here this is a thin film solar panel, solar cell. So here is very long. This is a chemical combination. It's very long. Thin film solar cell. So the energy efficiency is 20% efficiency, low material cost, potential low manufacturing cost. So here, they use the molybdenum substrate in this is in this story. So this is the film, and they just laser scribes. You just scribe this one. Right? Focus on P1 in this is the story. So here is this is the substrate. So here is the film, contact film, PV film, and contact film 1, film 2. So this is a focus of Gaussian beam. The Gaussian beam, I said, this is a distribution, energy distribution, and follows the bell-shaped the curve. So here, look at here, this waist diameter. So here is suppose this is the focal length, and we know that if from here to here, the spot is the smallest, and it goes down in this direction or in this direction, it is increasing. This is the diameter of the focal spot, and we use this one to calculate the diameter of the focal spot. And the focal length, we use this equation to calculate the focal length. So for the focal spot and focal length, and we get these values, right? And for this is the for their focal for their laser system. The focal depth becomes very short for small focal spot size, and this is accurate prediction of material surface at the focal spot becomes critical. So this is the very important. The generation of bezel beam. So this is a bezel beam. We know that it is the Gaussian beam. And here is generation of this bezel beam. So this is axial position. So this is intensity of zeroth order bezel beam. So this is I, and how to calculate this I, and using this equation. And the comparison of Gaussian and this bezel beam. So this is a bezel. So this is a Gaussian. You can see the huge difference. And the focal spot size, focal depth, and focal depth Gaussian, focal depth bezel, and they are listed here, and they are different. Experimental condition. So here is a TI software. And so here is the ND filter. This is XCOM. So this is a sample. And now they put this XCOM here. And the sample, and they have this molybdenum layer, and also this PI substrate. And so this is calculated, observed, determining damage threshold of molybdenum film and PI substrate. And you can for different laser, and also different for molybdenum and PI, different material, and they have different damage. This is different on the describe. Describe is based on this equation. Then here are the effects of the pulse energy and the scanning speed. So this is described. This is on this field. Right? This is 10 microjoule, 18 microjoule, 25, and 35 microjoule. So optical microscopy images of microgroups, fabricated microgroups here. And by this is different speeds and the laser power. You can see here is, if we use this is AFM, and you can see very beautiful. It's cool, very cool. AFM images of microgroups are fabricated at different scanning speeds and the pulse energy. The scanning speed means how fast you go. Right? Just because the beam remains constant, remains remains stationary, but the stage can move in x direction and y direction. So here is the impact of x-con tape and to sample distance. Here, from 2 micron, 2 millimeter, 3 millimeter, 4 until 18. And you can see difference, right? So these AFM images of micron groups are fabricated at different distances, either the sample surface and the x-con tape at the scanning speed and pulse energy at 15 micron group. So this is a cross-section of the subscribe. And they use this is the AFM cross-section. So here is, you can see here is the slot they subscribe, here is the slot they subscribe, and here is the slot they subscribe. For this one, and here are the summary for this is a thin film is the subscribing. Selective removal of molybdenum is possible because of difference in damage threshold and between molybdenum and PI substrate. So generalized generated from the x-con, the Bessel beam provides a variable way to greatly extend the focal range of this is a Gaussian beam. So experiments show that Bessel beam can provide fairly consistent groove quality while tolerating several millimeters of height. Fluctuations. The future work involves quantitative characterization of groove quantity, minimizing the heat effective zone, and optimizing operating these conditions. So this is the second research and already introduced. So beam shaping. We then talk about beam shaping using SLM. So micro machining on the borosilicate glass with various pencil beam shapes and beam shaping. So here you can see different beams on this is the borosilicate glasses. See, calculating the pattern is observe the pattern. So this is observe the damage. Scribing molybdenum film with zeros and 1 plus minus order pencil beam. You can see different. The scanning direction goes from this way to this way. Can reduce the damage from rims from the 0 order. The long focal range feature is retained. You can see it's very, very beautiful. This is much clearer than this one. And then we talk about femtosecond laser nanomachining of fused silicon and using ultraviolet infrared femtosecond pulse pairs. What should be an ideal laser nanomachining method? Single step and high dimensional control down to the nanoscale and high speed and surface and bulk. And these are for these 3D techniques. Approach to nanoscale. The nanoscale, the multiple beam interference, and single beam direct rating, and laser induced periodic surface structure. And we see, I showed you a picture. And fluence control, fluence is energy density. A high NA opticals, and this is short. This is a wavelength, and this is use this as ultraviolet. So this is fluid control. You can control it, and so here is NA equals 5. So this is the opticals. This is 65. So this lambda is 267 nanometer. And then Dolly used this femtosecond laser and to ablate the dielectrics. Decent process involved. So process involved ionization. It's a multiple multi-release of photon and tunneling occur. Electron avalanche and plasma absorption, shielding, energy transfer and to lattice and ferrodynamics is the shock waves. So here is a ionization model. Here's the ionization model. It's a multi-photon ionization. So this inverse, this is a square long. It's a collision ionization in average. So here's the concept of few wavelengths femtosecond laser nanomachining. And use a weak short wavelength pulse for seed electron creation through multiple photon ionization. And use a strong long wavelength pulse for electron multiplication through avalanche ionization. So here is MPI electrons. So this is a nanometer. This wavelength of this of laser. And so here is 800 nanometer. So this is avalanche of these electrons. And so here is the damage. You can see is the damage equator, and we degenerate the equator. The sample is fused silicon. Here's a dual wavelength enhances ablation efficiency, and the two wavelengths they have. So here is NIR only. So here is a 2 XUV and AIR, and you can see efficiency is much better than this one. So here is 1064 nanometer femtosecond, and so here is a 2, and you can see it's deeper, right? It also is a broader. So here is here is one wavelength, and so here is the dual wavelength. The dual wavelength has some diverse effects. You can see braking this direction rotates as a 400 nanometer pulse underneath increases relative to the 800 nanometer pulse from A to D. So this one, and this is signal enhancement for LIBS. So here is a UV, these are also two lengths. So this is only one wavelength. This is deeper. So their goal is to achieve nanoscale damage down to 10 nanometer and using electrically extremely short wavelengths like such as XUV radiation and reduce the damage threshold of the short wavelength pulse. So here is experimental setup for micro machining. So here's the stage, an XY stage, a sample CCD is the camera is used to monitor. Is a monitor here. So here this is a mirror. So here is the energy beam splitter, M1, ND filter, 2WP here, this is a mirror here. So here is another one. And these are two different ones, right? So here, this one, the dual, and this is the wavelength. The damage size is determined by UV score. So here is one wave, is another wave. The UV damage threshold is reduced. That means it is much easier to be damaged to remove the material. Is a dependence of UV diameter threshold on time delay, and different IR frequencies. So this is you can see here is a micro machine, and then we talk about this is a nano machine. This is nanometer, 800 nanometer. Here is a motor-driven delay stage. Damage approaching nanoscale. Okay. SEM image. Now here is the pulse. This is a cross section along the dashed line, along this line. Just have these 300 nanometer. The damage threshold versus delay. So this is a delay. So here is a threshold energy. The lower the better, right? So this is delay. If it's 0, it is much easier to remove the material. Here is the use of spatial filtering and to improve damage shape. So here's the experimental setup, and the P is a pinhole, RO is reflecting this objective RO. And so here is IFS. So this IFS is a sample, is a fused silica sample. The delta T mechanical delay line, and this is this one optical image of the pinhole used in the experiment. This one, sorry, this is a P. So this is UV damage threshold efficiency reduced for different energy level, micron joule. It depends on the delay. So here is the threshold energy. You can see here the energy level is lower. You can compare this one and this one. Okay? You can see this is alternate. The scale is changing. The wrong damage with large depths achieved. Large depths, wrong damage, wrong. You can see they want to have a wrong one and want to drill a hole. Deep holes are changed. So here's the summary. The UV pulse determines the damage size and shape, and with tightly focused UV pulses, 500 nanometer diameter craters are fabricated with a sub. This is a Newton. This is N2. N2 is nanojoule, and UV pulse under is very small. 90 to 95% reduction of UV damage and threshold is achieved, and with the assistance of the IR pulse at around zero delay. We know that we will see the future. IR polarization states are found to have similar effect on the UV damage threshold and the resultant damage shape. And high quality and efficiency nanomachining with feature size reaching 10 nanometer are maybe possible with shorter wavelengths, for example, as XUV, and optimization of the ionization process. So these are orderly acknowledgement. NSF, EOD, the Caterpillar, and research collaborators, and I published 2 papers with Orderly from this research, what I just showed you, the second one server. Any questions about this micron, this nano, femtosecond micron and nano machine? Are you guys entertained? Or are you guys digging? Digging? Okay.
Just a busy week.
Okay. So this is just to broaden your horizon, broaden your knowledge. Okay? Whenever there is some need, there is a need, say micro machining, you can just tell people that Paul told me about this is a later micro machining and nano machining. Okay, right? So this I might test your understanding, just as very conceptual things. After that, this is a problem statement, just go there to get the answer. No calculations,